today's class, we are going to discuss in detail about this divide and conquer strategy. And we will see two examples. One is that of merge sort, which you have already studied in your data structures course. And also in this course itself, we have discussed merge sort while discussing about recurrence relations. Okay. And the second one is an algorithm for matrix multiplication known as Strasson's matrix multiplication. Okay. So first, let's look at what is divide and conquer strategy. So this algorithm design technique, it solves the problem recursively. So what it does is that given the problem, it will be divided into subproblems of smaller size. Okay. So all these subproblems will be similar to the original problem. The only difference is that they will be working on a smaller input size. And this step is known as the divide step. Okay. And the second part is to solve the subproblems. So as is obvious, it is easy to solve a smaller problem compared to a larger problem. So if you have 10,000 numbers to be sorted, that's not very easy. But if you have like 2 numbers or 5 numbers to be sorted, it's an easy problem. Okay. So we will solve these subproblems, and this step is known as the conquer step. And the last step is to combine the results of the subproblems to get the solution of the original problem. Okay. So these are the 3 steps: divide, conquer, and combine. So we will study it in detail now. Okay. So first, let us look at what is the control abstraction. So what do you mean by abstraction? Abstraction means giving only the outline for the details are not specified. So this is basically an outline of how this divide and conquer works on a problem without giving all the details. Okay. So DAC stands for divide and conquer on a problem capital P. Okay. The first part is basically checking if the problem size is small enough to be solved directly, and if so, the problem is solved. Okay. If small of P, if P is of small size, then solve the problem P. Okay. Otherwise, what you do is to divide P into P1, P2, P3, and so on up to Pk. Okay. And then you apply DAC. This same procedure will be applied on P1, P2, and so on up to Pk. So there are k subproblems, and the divide and conquer procedure will be applied recursively to each of these k subproblems. Okay. So in the very first step, when you are dividing, the subproblems may not be of small size to be solved directly. But when you do it recursively several times, eventually you will reach that small size of the problem. Okay. And then you have to combine the solutions returned by divide and conquer on P1, divide and conquer on P2, and so on, divide and conquer of Pk. So this is just an abstraction or outline of how this divide and conquer procedure works. We will look at examples and then it will become more clear. But from an examination point of view, you can actually try to memorize this control abstraction also. You may be asked to explain the control abstraction of divide and conquer strategy. Okay, again, representing the same thing as a flowchart. So we are given an original problem, which is divided into, in this example or in this figure, we are dividing the original problem into two subproblems. Okay. And then each of them is solved separately, which is a conquer step. And then you have the combine step that combines these solutions to get the solution to the original problem. Okay, so what are some examples of problems that use divide and conquer? Okay. So you have seen some of them already. So first one is binary search. So you are familiar with how binary search works, right? So you have an array. So can someone tell me, will binary search work on all arrays? Or is there any property that the array should satisfy for binary search? So binary search means basically we are searching for an element in the array. Okay. So can someone tell me what is the requirement that should be satisfied by the array so that we can apply binary search to search for an element? Any guesses? Okay, someone please, if you know the answer, please unmute yourself and speak. Okay, let me ask the question. If the array is not sorted, can we apply binary search? Yes or no? So nobody is there or nobody knows the answer?
No, ma'am.
No.
Yeah. Okay, fine. So the condition that I was looking for is that the array should be sorted. Okay. So once you have a sorted array, what you can do is that you can split it into two parts, and depending on so you have to look at the middle value in the array. Okay, and compare it with the element that you are searching for. So if the element is less than the middle element, then you can search in the left half of the array. Otherwise, you need to search only in the right half of the array. Okay, and this will get repeated until eventually either you find that element or you conclude that the element is not present in the array. Okay, so basically you will go on. If you find the element, then you stop immediately. Otherwise, you will repeat this splitting of the array till you reach like an array of size 1. Okay, so that is how binary search works. So this is an example of a divide and conquer problem. And next example is the maximum subarray sum problem. Okay, so what is this problem? So you are given an array of integers. It could consist of positive as well as negative integers. And now you need to find out what is the maximum sum of a contiguous region of the array. Okay, so you have to find the sum of the consecutive elements in the array, which is maxima. Okay, which is that subarray that has the maximum sum. You have to find out the sum of that subarray. Okay, so this also can be solved using this divide and conquer approach. So we are not going to discuss that in detail. So you can just look it up. You can try it on your own. And then maybe we can just look it up how we can apply divide and conquer strategy for solving this specific problem. Okay. So two problems that we will consider here are merge sort and Starsen's matrix multiplication. So quick sort, which you have already studied, is yet another example of divide and conquer strategy. So now let us go into.
ഒരാളെ കൂടെ ക്ലാസ്സിൽ കേറ്റാനുണ്ടോ ഒന്ന് കേറ്റാവോന്ന് ചോദിച്ചു.
Okay, yeah, sure.
Thank you, ma'am.
Yeah. Okay, so let us continue. So here you can see an example of an array. Okay, this 40 is placed below, but it's also part of the array. So there are actually 7 elements in this array. Okay, so yeah, you need to get this array sorted. So how does merge sort work on this array? So let us look at the illustration. So first you will divide this given array into 2 parts. Okay, so the original problem is divided into 2 subproblems. About the so this splitting is done around the middle element. Okay, so this is having if there are even number of elements in the array, if the number of elements in the array is even, then you will get 2 arrays of the same size. Because in this given example, there are odd number of elements. You have one array of size 4 and another array of size 3. Okay. So, and then this will be repeated, or this will be done recursively. Okay. So next, you split this array of size 4 again into 2 parts, each of size 2. And similarly, okay. And then again, the array of size 2 will be splitted into 2 arrays, each of size 1. Okay. So once you reach the array size 1, okay, then you consider that the problem is small enough, okay, to be solved directly. So at that point, you have to do so basically an array of size 1 is sorted in itself. Okay, so there is no sorting required on an array of size 1. So you just return that array as such, and then the next step or the combined step involves basically given 2 sorted arrays, it will merge these 2 sorted arrays into a single array. Okay, so that is the combined step in this merge sort. We'll look at the algorithm after this. So once you reach the array of size 1, you will start this merging step. So merging means basically you are given 2 sorted arrays and you have to combine those into a single sorted array. So here you have 100 in the first array and 20 in the second array. So when you do the merge operation, 20 is less than 100. So 20 will be placed first and then 100 will be placed after that. Okay, the same thing happens on the remaining part. Okay, so this array of size 2 will be splitted into 2 arrays of size 1 each, and then you do the merge operation to combine those 2 arrays. Okay, and now you have 2 arrays of size 2 each. Okay, you need to combine them also. You have to merge these 2 sorted arrays. Okay, so we'll study about how the merge operation works. Essentially, what it returns is the it will return the elements in both the arrays in sorted order. Okay, so thus you get this sorted array of size 4. So the same thing happens on the right half of the array also. Okay, so this array of 3 elements, it gets splitted into 2 parts, one of size 2 and the other of size 1. Okay, and the size 2 array will be again splitted into arrays of size 1 each. and then you have the merge step, and now one more merge step. Okay, so that this right half of the original array is also sorted now. Okay, and the last step is to combine these two sorted arrays. Okay, so thus you will get a sorting of the original array. So this is how merge sort. This is just an illustration of merge sort on an example array. So now we will look at the algorithm. So let us say our array is A. Array A, starting index is low and the last index is high. Okay, this is the global array which is to be sorted. And this merge sort algorithm, it takes this indices, starting index and the last index of the array as inputs, and then it checks whether low is less than high. Okay, if low is less than high, that means the array is having at least two elements. Okay, when this condition is violated, that is when basically you have an array of size 1. Okay, so when the array is of size 1, then you don't need to do anything. There is no sorting to be done. Okay, so that is why you have this condition if low is less than high. Okay, so what do you do? First, you calculate the middle point. Okay, as low plus high by 2. Okay. So actually this can be a floating point value. Okay, but you are taking only the integer part. Okay. So if low plus high is coming out to be an odd number, in that case also you will be taking the integer part of this division of the answer. Okay. Yeah. And once you calculate the mid value, you call this merge sort recursively on the left half as well as the right half. Okay, so now when you call recursively, you need to pass the starting index and the last index of the left half of the array as well as the right half of the array. Okay, so left half, for the left half, the starting index is low itself and the ending index is going to be mid. Okay, so the array portion from low till mid is considered as the left half of the array, and the remaining part of the array starting from mid plus 1 and going on till high. So that will be considered as the right half of the array. So you have to call merge sort recursively on both these subarrays, left subarray as well as the right subarray. And then you have this combining of the solutions that is happening in this merge step. Okay, so merge requires 3 arguments or 3 inputs: the low, the mid, and the high. Okay, so basically you are combining A of, so once you do this recursive calls, so A of low to mid, okay, or the left half, that becomes sorted. Similarly, A of mid plus 1 to high, the right half, that also becomes sorted. And now you have to merge these two sorted arrays. So that is why you require the merge operation. Okay, so this algorithm is not complete because we have not specified how to do the merge operation. So you need to add that also. But this is the outline of the merge sort algorithm. Okay, so this is an explanation of this condition if low less than high. So we are going to consider that the problem is small when there is only one element in the array. Okay, so and in that case, the array is already sorted. Yeah. So now we are going to look at the algorithm merge. Okay, the merge operation within merge sort. So here, first I will explain what are these inputs, low, mid, and high. So we have already talked about that. So basically, A of low to high is a global array that contains two sorted subsets. The left half is also sorted, right half is also already sorted. So left half is there in A of low to mid, and right half is there in A of mid plus 1 to high. And the goal is to merge these two sets into a single set or into a single array in A of low to high. Okay, so how we do the merge operation is we will use an additional array. So merge sort has some additional space requirement. So you have already studied, I think, about in-place sorting and all that. So merge sort does not sort the array in place. It actually creates a temporary array, okay, and that will be used for merging this left half and the right half, and then after storing the sorted array in B, you will be copying it back to A, so that A becomes sorted. Okay, so we will see that as we look at this procedure. So there is additional space requirement. So if the original array has n elements, there is an additional space requirement of order of n for big O of n for this merge sort procedure. Okay, so B, the name of this temporary array that we are going to use is given as B. Okay, so here we will maintain 3 pointers. Pointers means not the pointers that store memory addresses. So basically to keep track of the indices. Okay, so we need one variable to keep track of indices in the left half, and the variable to keep track of the indices in the right half, and the last variable is used for keeping track of the indices in the auxiliary array, okay, or the array B. Okay, so h equal to low, h which is initialized to low, that is keeping track of the indices in the first half, okay, left half of the array, and j equal to mid plus 1. This will be keeping track of the indices in the second half, and I equal to low. This is going to keep track of the indices in the merged array. Okay, so the first part is while h is less than or equal to mid and j is less than or equal to high. So basically you are comparing the elements in these subarrays one by one. Okay, so first you take the first element from the left half and you compare it with the first element in the right half. Okay. And when you compare, if A of H is less than or equal to A of J, okay. If whichever is the smaller element, that you will store it into B, okay. P of I is equal to A of H. So if A of H is smaller, that means the element in the left half is smaller, then you will store that smaller value into B, and then you increment the index H equal to H plus 1. Okay, so you will go to the next element in the left subarray. Otherwise, suppose the element in the right half was smaller, then you do P of I equal to A of J. So you store that whichever is a smaller value that you will store in the auxiliary array, and you increment the corresponding index. And you also need to increment the index in the array B. Okay, because in the next iteration, you have to store in the next position. Okay. So this will happen. This will be repeated as long as h is less than or equal to mid. That means you have not reached the end of the left half, and j is less than or equal to high. That means you have not reached the end of the second half. Okay, so as we already told, these two subarrays, left and right, they may not be of exactly equal size. Okay, if the number of elements in the original array is even, then you will get the left array and the right array to be of the same size. But otherwise, there could be a small difference in the size of these two subarrays. So one of them could be having one element more than the other one. Okay. So that is why you are giving this condition. Okay. And so let us say first array is having 4 elements and first half is having 4 elements and second half is having 3 elements. So this loop will run as long as you process 3 elements from okay. Or like till you do not reach the end of either array. Okay. Yeah, once you reach the end of any of these arrays, left one or the right one, you will exit out of this loop. And then again, now what you need to do is whichever is the array that is not yet completed, whichever half is not yet completed, then you just need to copy it into the array B. Okay. So that is done in steps starting from 10 to 15. Okay. So if H is greater than mid, that means H was the variable that we used to keep track of the indices in first subarray. So that means if H is greater than mid, that means first subarray is already processed. So already the elements in that is stored into the array B. Okay. Then you need to only copy the elements from the second half. So that is why you have this loop. For k equal to j to I, do b of I equal to a of k and I equal to I plus 1. So whatever is remaining in the second part, you will copy it into the array B. So otherwise, suppose second array is completely copied. So in that case, you need to copy the remaining elements in the first array. So that is why for k equal to h to mid, do b of I equal to k and I equal to I plus 1. Okay. Yeah, now the last step is you have to copy the, you are having the sorted elements in the array B, which is a temporary array. So you need to copy back those sorted values or the values in sorted order to the original array, which is A. So that is why for k equal to low to high, do A of k equal to B of k. You are just copying back the elements from the array B to the array A. Okay, so maybe we can look at the example once again. Okay, so I will explain that merge procedure with respect to the these two subarrays. Okay. So here you have 15, 20, 30, 100, which is already sorted. Then you have 5, 40, 75. That is also already sorted. Now suppose you are calling this merge operation on these two subarrays. Okay. So what? So you have the pointer h on the variable h. Just keeping track of the indices here. And then you have the variable, what was the variable? J. Yeah. The variable j that is keeping track of the indices in this right subarray. So first to compare A of h with A of j. Okay. So you see that among 15 and 5, 5 is smaller. So that means you will store this 5 into this array B. Okay. So you will store 5 and you will increment the index here. Okay. So you will go to the next element in this. So now you will compare 15 with 40. Okay. So here the index is not incremented. So here you are still at 15 and here you are at 40. 15 with 40, 15 is smaller. So 15 will be copied into the array B. Okay. So because you have taken the element from this, you will increment the pointer here. So you'll now move to the next question, which is 20. So in the next iteration, you will compare 20 with 40. Okay. So 20 with 40, 20 is smaller. So 20 will be copied. And the pointer here will be incremented. Okay. So next you will compare 30 with 40. Okay. So 30 with 40, 30 is smaller. So you will copy 30 here and you will increment the pointer. So you will reach this position 100. So now we will compare 100 with 40. So 40 is smaller. So that means you will copy 40 Okay, and increment the pointer to 75. So compare 75 and 100. 75 is smaller, so 75 will be copied over here. Okay, so now you are done with this second array. Okay, so when you try to increment the pointer, you will actually go out of range. So that means you will exit from that while loop. And then you see that there is one more element in the first half to be copied. Okay, so you will just copy that directly to the array B. Okay, so this same step is happening in all these intermediate stages also. So this merging step is happening in the intermediate stages also because of the recursive manner in which we have written the algorithm. Okay. So now let us look at the time complexity of the merge sort. This we have already seen actually when we discussed about recurrence relations. I gave an example that is arising from an algorithm. Okay, so this was the example that we discussed at that time also. So here T of n is representing the time complexity of the algorithm when run on an array of size n. Okay, if the number of elements in the array is n, then the time complexity of merge sort is given by T of n. Okay, and by looking at the algorithm, we can say that T of n is equal to 2 times T of n by 2. Okay. Why T of n by 2? That is because we are splitting the array into two parts, each of size n by 2. Okay. And then you are recursively calling the same algorithm on each of these two parts. Okay. That is why 2 times T of n by 2. And then you have the merge operation, right? So you have to merge these. So there are two arrays, each of size n by 2. Both of them are sorted. And then you need to merge these two subarrays. So the time complexity of that will be big O of n by 2 plus n by 2. Okay, each of these arrays are of size n by 2. So that is why you have big O of n by 2 plus n by 2. Okay, so that is represented by n by 2 plus n by 2 is n. So big O of n by 2 plus n by 2 is represented by this factor C times n. C is a constant. Okay. And this expression is true whenever the value of n or the number of elements in the array is greater than 1. Okay. So if the number of elements in the array is equal to 1, then actually you are not doing anything specifically in the algorithm. You are just returning it as such. So the time complexity of that is represented by under constant A. Okay, now you can apply any of the techniques that you studied for solving recurrence relations. Master theorem is applicable, and you have other methods like iteration. I think this is a problem that I have given in the assignment also to solve using iterative method and substitution method. Okay, so anyway, the answer will come out like this. T of n equal to big O of n log n. So maybe you can just look at these steps. That is trying to solve this equation using iterative method. Okay. So iterative methods means you will expand T of n by 2. T of n by 2 will be 2 times T of n by 4 plus C into n by 2. And you substitute it into this original equation. Okay, so then you will get 4 T of n by 4 plus 2 into Cn. Again, you will expand T of n by 4. And then you repeat this and you find the pattern. Okay. Basically, we get 2 raised to k into T of n by 2 raised to k. Okay. Plus k into Cn. Okay. And now you find out when you equate n equal to 2, basically you need to find out the value of k. For that, you can put n by 2 raised to k is equal to 1, or you will get k equal to log n to the base 2. Okay. So that is why T of 1 is equal to T of 1 is the time is actually given in the recurrence relation itself. It is given as when n equal to 1, the value of T of n is A. Okay, so that means T of 1 is equal to A. Okay. So basically, U raised to K is nothing but n. So n into A. T of 1 is A. And then you have Cn multiplied by K. But K is log n to the base 2. So that is how you get T of n equal to big O of n log n. Okay. You can use master method also. Using master method also, you will get the same answer.